All right, so I think it's 12:20 Eastern time. So welcome back to the last session of today. So the moderator will be Maria Emilia De Rossi. So please go ahead, Maria Emilia.
Thank you. Welcome to our last session of this exciting conference. We will start with two contributed talks about 8 minutes each and 2 minutes for live questions. Please post your questions about a given talk in the Q&A tool or raise your hand. Our first speaker is Jussi Kuusisto, who will talk about active galactic nuclei in first light and reionization epoch simulations. Please go ahead.
Thank you. Hopefully you can see my slideshow now. And yeah, my name is Jussi. And yeah, thank you for this opportunity to talk to you about active galactic nuclei in the first light and reionization epoch simulations, or flares. And I also have a recorded talk, so if you find this interesting, please check that out for more details. But I'm going to just recap the sort of highlights here. So I'm just going to jump into it and describe the simulations themselves. So flares is a suite of 40 resimulation suites of 40 regions picked from this huge dark matter only parent box. And this schematic gives gives a comparison between the parent box in the background to the blue tides volume, as well as the Eagle 100 megaparsec box. These 40 regions were picked based on their density compared to the average density in the parent simulation. So this allows us to simulate a wide variety of different environments. And they were the regions themselves were resimulated using a variant of Eagle simulation physics down to just below redshift 5. So yeah, this strategy allows us to simulate, for instance, the most dense environments in the parent simulation, and thus probing a higher effective volume. And so finding objects that otherwise, in an equivalent periodic box wouldn't exist. And the strategy also allows us to combine the individual regions into composite, for instance, luminosity functions. And showing you an example of that here. So this is a redshift 6 luminosity function for flares in solid lines and Eagle reference volume in dashed lines. And as you can see, flares sort of extends us into the higher luminosities at the bright end. And the top panel then is showing you the actual number of simulated galaxies in these two simulations. As you can see, again, the increase of flares over the Eagle reference volume is especially relevant towards the higher luminosities. I'm putting that increase in a little bit differently. So here I'm plotting showing the cumulative number of simulated galaxies as a function of their stellar masses in the simulations, flares in solid lines and Eagle in the dotted lines, and then color-coded by redshift. So from this, you can see that, for instance, above 10 to 10 solar masses at redshift 5, flares has about 20 times as many galaxies as exist in Eagle. And this becomes even more relevant towards higher masses, where flares simulates galaxies that do not exist in Eagle simulation. So yeah, this becomes relevant for rare objects such as AGN, this is talking about, as well as it's a good companion for upcoming sort of making predictions for upcoming wide area surveys. So on to the actual AGN in the simulations. What I'm showing you here are the AGN luminosities as a function of their black hole masses for various redshifts. So the circle dots are showing the flares objects. In teal sort of diamonds, I'm showing the Eagle objects in these ranges of luminosity and black hole mass. And then the stars are giving a small sample of actual observational quasars at above redshift 6. So as you can see, the sort of flares contribution is increasing the number of sort of higher luminosity AGN that we have compared to Eagle again, as well as pushing towards where we actually are observing high redshift quasars. And this also allows us to look at the bolometric luminosity functions. So what I'm plotting here is the AGN luminosity function in flares in dashed lines, and in dotted lines I'm given the host galaxy luminosity functions, and then the solid lines is giving the total object, so contribution from both the AGN and the stellar component of the host. So as you can see, the AGN do elevate the number densities at the extreme bright end compared to just the sort of host galaxy on its own. And we can look at UV luminosity functions as well. So here I'm plotting AGN dust attenuated luminosity functions in dotted lines. At the intrinsic AGN UV luminosity functions in dashed lines, and the dust attenuated host galaxy luminosity functions in solid lines. So as you can see, the dust attenuation gets the AGN quite badly, and there's a few reasons for this, which one of them is that the most massive galaxies in flares are quite compact, and their sort of dust is concentrated around the center of the galaxy. So thus it affects the AGN more than it does stellar particles around the galaxy. So yeah, I wouldn't say that the dusty AGN really contributes towards the total luminosity functions anymore in the UV. We can also see whether the AGN in these simulations are showing their host galaxies. So here I'm plotting the AGN bolometric luminosity divided by the host stellar bolometric luminosity, and this is log 10 of that relation. So the dashed line of 0 gives the 1-to-1 correspondence. Thank you. As a function of stellar mass of the galaxy, and the lines then give the median of this relation, and the shaded region gives the central 68th percentile range. And the scatter plot above that 1-to-1 correspondence line gives the individual objects where the AGN are more luminous than the host galaxy, again in bolometric luminosities. And kind of as sort of you could see from the luminosity functions in attenuated UV luminosities, this kind of changes around. So there's literally a handful of AGN where they still outshine their hosts in dust attenuated UV. But as I said about the most massive galaxies getting more dust attenuation towards the center, so this is why sort of the AGN gets more attenuated than the stellar components. So hopefully we've seen from this that flare starts to cover the regime where AGN are beginning to outshine their host galaxies, and as well as probing towards the luminosities of the observations at high redshift. But it doesn't yet fully cover the domain where AGN actually dominates the sort of bright end of the luminosity function, for instance. So on this point, flares 2 simulations are currently in development, and they're going to simulate a larger volume, and doing so with an improved physics model and hydrodynamics. And that's basically it for me, but I just wanted to say that if you find any of this interesting, see the recorded talk. And I also wanted to point out that we simulated some of the regions twice, once with AGN feedback turned off. So that allows us to study what effect the AGN actually have on the host galaxies they reside in. Thank you.
Thanks for such an interesting talk. We have time for questions. I don't see questions in the Q&A, and I don't know if anyone is raising his or her hand. Well, I have a question. I understand that flares include a similar AGN model as Eagle, and as a redshift 5, for example, is there agreement with the prediction of Eagle regarding the black hole mass velocity dispersion relation, which is in Eagle calibrated at redshift 0?
That is an excellent question. I can't from the top of my head answer that. I apologize. But it is using the same physics, so it should sort of agree with Eagle. Yeah.
Okay. We have time for one quick question. If someone have any question? No?
I think there's a hand up in the...
I have a question. So these are Zoom simulations, right?
Yes. They're simulating basically the same resolution, but with full hydro.
Yes, but these are like extracted from a large dark matter only simulation,
yes,
and zooming into a region. So I was just wondering how did you compare your number of galaxies with Eagle simulation? Did you compute like a number density?
Yeah, so that was the point about like essentially knowing how to pick the regions. We sort of introduced in the Chris Loventhal paper mentioned here, a sort of weighting scheme. So knowing how the environments sort of are spread, like what the spread of different overdensities of the same size are in the parent simulation. We use that as a weighting scheme to weight the individual regions' contribution to, like, for instance, the distribution functions.
I see. Thank you.
Well, thank you very much. We have no more time for questions. The discussion can be continued in this Slack chat. Well, now we can, let's move to the second talk. The next speaker is Joanna Piotrowska, who will talk about putting brakes on star formation, evidence for the integrated effects of historiation feedback.
Yep, thank you very much. Well done on pronunciation of my last name. Can you see my screen? Double checking. Is that fine? Yeah, okay, great. Splendid. My name is Joanna Piotrowska, and I'm a final year PhD student at the University of Cambridge, where for the past 3 years, I've been researching the question of what physical processes drive star formation quenching in the local universe. And I am taking a step back from these exquisite high resolution and high redshift studies to take a broader look at what AGN or any physical processes indeed can do in order to stop star formation. So to set the stage, very briefly, let me remind ourselves that galaxies in the observable universe can be divided into two broad categories: blue star forming and red quiescent. And these two populations are fundamentally different for a sort of different reasons. And they have different structure. They're dominated by different stellar populations. Some have dust and gas, some don't. But most importantly, blue galaxies are on average star forming and red are quiescent. And as observed across cosmic time, these two are interpreted as an evolutionary sequence in which blue star forming galaxies transition to become quiescent in a process called galaxy quenching. And before I go any further, I would like you to remember two takeaway points from my talk. First of all, that AGN feedback is most likely responsible for quenching in massive central galaxies, i.e. this transition from blue star forming to red quiescent, and that it is the integrated history of AGN feedback as traced by black hole mass, rather than instantaneous AGN activity that ultimately determines the star-forming state of a galaxy, massive central galaxy, at redshift 0. To give a broad overview of what we know about quenching already is that I have to say that it has already been shown over the past 2 decades to correlate with a slew of galactic properties, starting with galaxy stellar mass. The more massive you are, the more likely you are to be quenched. Similar with galactic environment, the denser it is, the higher chances for quiescence. Similarly with morphology, more pronounced bulges, higher chances of being quenched, and most recently, dynamically measured estimated black hole masses at the centers of galaxies. Now, all of these relationships are just observational consequences consequences of real physical processes that ultimately cause galaxies to stop forming stars. And you can go about it really in two ways. Either by removing fuel for star formation, no gas, no stars, or you can have plenty of gas available, which for some reason is prevented against gravitational collapse. And on the side of lack of fuel, we have a fair share of observational evidence for different phenomena occurring at different scales, including gas removal via AGN in outflows we've heard a lot about, or heating by AGN we've also heard about before over the past 4 days. On the side of decreased efficiency, the image is a little bit more blurry in the sense that we do not have good observational evidence. But what we're trying to do in our research is we're trying to answer the question of which of these processes is really the key responsible for ceasing star formation, focusing on massive central galaxies. And in order to do that, we set up, if you will, an experiment in astrophysics in which we take theoretical predictions from 3 publicly available cosmological simulations, Eagle, Illustris, and Illustris TNG, and then compare them with the observable universe as seen by the Sloan Digital Sky Survey. It also so happens that all 3 simulations share the same simulation box volume and implement 3 different prescriptions for their AGN feedback mechanism. They're, of course, schematically summarized in the slide, but to give a brief overview, in Eagle, we've got, if you will, a quasar mode feedback injecting heat. In Illustris, at high accretion rates, we've got quasar mode. At low accretion rate, we inject bubbles, or the simulations inject bubbles into the IGM end. In Illustris TNG, the situation is similar with the replacement of low accretion mode, which instead introduces random momentum kicks around the black hole. Now, thanks to these differences among these simulations, we can actually derive theoretical predictions for the observable consequences of different AGN feedback quenching mechanisms. And it's not only about AGN feedback, really. I mean, we know it is a fairly good suspect in killing galaxies. However, there are other processes that can be potentially responsible for ceasing star formation when it comes to centrals. Among those, we also have supernova feedback, or a virial shock heating as gas streams through massive gravitational potential wells and shock heats in the process. So what we decide to do in our experiment, we identify 3 main parameters connected to those processes: black hole mass for AGN feedback, halo mass for virial shock heating, and stellar mass for supernova feedback, and then use a method appropriate to grasp all the complexity associated with the nonlinear process we call quenching. And that is, surprise, surprise, machine learning, or in our case, random forests. You've heard a fantastic talk about random forests earlier yesterday, I believe. However, if you'd like to learn more, I have a detailed chunk of that in my extended recording of the talk. But to give a brief overview why we think this particular algorithm is relevant for our study, there are several, 4 to be precise, straightforward reasons. First of all, random forests are very easy to implement. Because they are a straightforward algorithm. And because they are so straightforward, they're also no longer a black box tool, because we can directly trace the logic behind individual decision trees. Hence, we can easily imagine the path taken by the algorithm to reach the final decision. The random forests also allow us to extract, directly calculate the importance each of given galactic parameters carries in order to determine whether a galaxy is star forming unquenched, and most importantly, as shown recently by Asa Block, my PhD supervisor, these random forests not only extract relationships between the final classification and the input parameters, but most importantly, they extract the causal ones, hence helping us in addressing the question, correlation does not imply causation. So in simulations, all those 3 parameters are obviously readily available. However, it is a bit more difficult in the observations, especially when it comes to black hole mass. And in order to overcome this difficulty, we use a series of relationships found observationally between dynamically estimated black hole masses, y-axis, and different galactic parameters. Among the three, stellar mass, bulge mass, and central velocity dispersion, the central velocity dispersion black hole mass relationship is the tightest one. And so in our research for Sloan, we use central velocity dispersion estimated black hole masses as input parameters in our random forest. So the most important takeaway, number one, is presented in the slide. I'm showing you the relative importance of each galactic parameter, black hole mass, stellar mass, and halo mass, for determining the passive star-forming classification of galaxies at redshift 0, simulations on the left-hand side, observations on the right. And if you focus on the simulations, you will see that it is beyond any doubt black hole mass that is the most important parameter for determining the final classification. And this result is true in all three different simulation suites, regardless of the exact implementation of AGN feedback. Now, if you go over to the observations in Sloan, you'll see that this theoretical prediction on the left-hand side is matched almost overwhelmingly well in the SDSS, regardless of the black hole mass calibration we decided to use. So that is take. Yes. 2 minutes. Is that correct? Right. So that's
we have time for questions now.
All right. Yeah. So in that case, I'll skip the last slide because I'm out of time. Is that correct? I just couldn't hear the warning of 2 minutes, but that's fine. So we're at the conclusions at this point, where hopefully I managed to say that this result that I've shown on the previous slide is a convincing demonstration for AGN feedback being truly responsible for quenching in massive central galaxies. And what I didn't get to show, but hopefully you get to hear in the extended talk, is that it is the black hole mass rather than instantaneous accretion rate onto the black hole that ultimately determines the final classification. And I do apologize for running over time. Got a little bit confused without the warning.
Don't worry, I said 2 minutes, but perhaps there is a technical problem with the audio. I don't know. But well, thanks very much for such a nice talk. I think that we can accept one quick question. Someone raised the hand. Darren. I don't know if you can talk.
Yeah, can you hear me?
Yes.
Yeah, so very nice results. So, you know, as we know, for black holes and galaxies and dark matter halos, you can have a common final state, but they can take very different paths through their history to get there. Some grow early and some grow late. And so what is it about this cumulative effect that makes it robust against these different paths from your research and what you've been doing?
That's an excellent question. Thank you very much. I think it is an indication of sort of, if you will, I can't really call it local because I would imagine that AGN do influence galaxies around them. So I think it is a manifestation that what really matters is how much energy the AGN outputs over the entire history of the galaxy into the IGM, preventing potentially offsetting gas cooling and preventing its collapse onto the galaxy itself. And I think it is just a statement that this might be one of the main reasons for which galaxies stop forming stars. It doesn't go to say it is the only one. It may be one of the more relevant ones. And in fact, touching onto the histories, different histories that the galaxies have taken throughout the time, I wanted to say that there are works in the process that look at the accretion history of the AGN and trying to connect it with the present star forming / passive state of galaxies, finding that depending on the implemented model, it might actually be the peak in the Aegean luminosity, historic Aegean luminosity, that actually determines the classification rather than black hole mass integrated over time.
Okay, thanks.
Well, thank you very much. The results are very, very interesting, but now we should continue the discussion via Slack. I think that you have more questions, so pay attention to Slack. Now we have the poster session. We have 1 minute for each poster, and any question should be asked and answered by Slack in the case of posters. Well, all the posters were uploaded to Slack, and when I think that we can start with the first poster presenter, who is Akland Bolnik. Please go ahead.
Thank you, Maria. Hi, everyone. So my poster presents results from a recent work led by me where we probe the formation of the most luminous redshift 6 quasars in a universe with illustrious TNG as the underlying physics. But we explore a wide range of black hole seeding as well as accretion models. We simulate some of the rarest, most extreme overdense environments in relatively small simulation volumes and high enough resolution using a technique called constrained Gaussian realizations. The figure to the left basically shows a gas density field of an example region at redshift 6. And it forms a very massive 10 to the power 12 solar mass halo at redshift 6, which is much more compact than a typical halo of the same mass. And these highly compact halos produce the most rapid black hole growth, even more so than further more massive halos that are not as compact. So these regions are essentially the most promising to produce luminous high redshift quasars. We then go on to show that the black hole growth in these regions are strongly sensitive to the seeding as well as accretion models, as you can see in the middle and right figures. And only few of these models are able to produce 10 to the power 9 solar mass black holes by redshift 6 consistent with the observed quasars. We then go on to identify specific conditions under which our models produce these redshift quasars, which includes early growth via black hole mergers or superheterogeneous accretion. For more details, please feel free to refer to my poster. I'm happy to answer any other questions you have.
Many thanks. The next poster is by Ilya Wilkin. Sorry if I pronounce bad the name.
That's okay. Thanks. Hello, everyone. I want to in my poster I summarized our recent results on inferring the quasar lifetime distribution. As many people, we use the quasar proximity zones, but we use helium-2 proximity zones, which are sensitive to a longer time scales of accretion episodes on the quasar. And we also built our so these results are built on several papers that we published before on individual quasars, where we were trying to infer the individual lifetimes. But I must say that all the proximity zone measurements actually deliver the lower limit on the quasar lifetime, because you never know if the quasar will continue shining after you observe it. And so we take into account all these stochastic connections between the lower limit that you measure from proximity zones and the actual underlying shape of the quasar lifetime distribution, and using the MCMC and the cosmological, hydrodynamical, and radiative transfer simulations, we infer the distribution, which is shown here in the bottom plot. And we also make some cool predictions about, for example, finding the probability of finding the so-called young quasars that are reported at redshift 6. And so please go and check my post if you have more questions. Happy to answer. Yeah.
Many thanks. The next poster presenter is Marco Alfonso Alban Morales. Please go ahead.
Hello, thank you. Yeah, so nowadays we have many ways to detect AGNs. So our main goal here is to investigate how the kinematics or AGN feedback signatures depend really on these selection methods. So studying this will help to unravel the role of AGN selection when studying AGN feedback, and to investigate these intrinsic differences between different AGN populations. So we use the whole manga survey, and we develop a method that extracts the radial profiles of an emission and width parameter, which is named W80 in the y-axis of my plot. So we average these radar profiles for optical AGN candidates and for non-optically selected AGNs. So this is what we find so far as preliminary results. We find that all differently selected AGNs in the color lines have enhanced radar profiles when compared to normal or standard star-forming galaxies and when compared to the whole Magnus orbit. So yeah, my name is Marco Van, and I encourage you to go to my poster and see further information and my contact also. So thanks.
Many thanks. The next presenter is Jussi Choi. Please go ahead.
Hello, my name is Joseph Choi. I'm a PhD candidate at the University of Oklahoma. So my poster describes some of the selected results from the first systematic study of a large sample of iron low ionization broad absorption line quasars, or Fe low bulk quasars, where we analyzed 50 STS spectra of low redshift objects using our group's spectral synthesis code symbol. So these objects represent a subgroup of bulk quasars that have the highest column density outflows, and thus they're excellent targets to study powerful winds that can potentially power feedback and quenching. So from our work from the sample, we found that these Fe low bulk outflows are located in a wide range of distances from the central supermassive black hole, spanning more than 4 orders of magnitude from some close by outflows in parsec scale, or some located out in tens of kiloparsecs away from the central supermassive black hole out in host galaxy. Moreover, we found a very wide range of mass outflow rates and also momentum flux ratios. And when looking at the distributions of these properties and the correlation analysis from this work, we found a tight correlation between the locations of the winds and the outflow velocities when excluding this new class of outflows that we defined, that we named loitering bells. And also there is we found a positive correlation between the quasar outflow luminosity, quasar outflow velocities and the quasar volumetric luminosities. And I encourage you to check out my poster to see what other exciting results that we found from this project. And feel free to reach out to me via Slack if you have any questions. Thank you.
Thank you very much. The next presenter is Karen Lightly. Please go ahead.
Hi, I'm Karen Laley from the University of Oklahoma. I'm Joseph's thesis supervisor. So it turns out that 30 of the low redshift iron low bulk quasars that he did the spectral synthesis modeling for have a sufficiently low redshift that H beta appears in their SDSS spectra. So what we did was we modeled those spectra and extracted the black hole mass, et cetera, along with a sample of 132 unabsorbed comparison objects. And our principal results are that the unabsorbed objects and the BAL objects are different. So in particular, the BAL objects are split into 2 types. There's a low accretion rate type and a high accretion rate type. And there are few intermediate types. In fact, it does actually successfully pass a bimodality test. And so then we looked at the 2 different types of BAL quasars, the low accretion rate and the high accretion rate. We found that there's a lot of differences. The plots show that the high accretion rate ones have fast outflows close to the nucleus, and the low accretion rate ones have very low outflow velocities close to the nucleus. Those are actually the loitering outflows that Joseph talked about. The bottom line of this work is that we're seeing a lot of evidence for a range of properties of BAL quasars. The first really evidence that we've been able to extract in the 40 years history of this topic, where outflow properties depend on the accretion rate and on the location in the quasar. And altogether, there's more details in the poster and also in 3 submitted papers, which are linked to my poster, that we're looking at different confinement and acceleration mechanisms. And the broader impact potentially is that we're going to be able to actually solve the astrophysics of BAL outflows ultimately.
Many thanks. The next poster is presented by Priyanjali Patel. Sorry if I pronounce the name bad.
Don't worry. Thank you, everyone. Hello everyone. My name is Priyanjali Patel and I am a PhD student in Universidad de Chile. Next, please. So here in this, the topic of this poster is to study the variance as a function of the rest frame wavelength. And to understand this briefly, in the right side, this is a Keplerian accretion disk, and in the center, this is the black hole. And we expect that this accretion disk follow a temperature profile. So the smaller regions should emit the more luminosity. And in addition to this, in the bottom panel, if you see in the orange, there is a corona that is just situated just above the black hole. So we expect that there should be a reprocessing going on by the accretion disk of the corona X-ray. So in this project, we want to understand what is the mechanism behind this accretion physics, and also we want to understand which process play a key role behind this accretion mechanism. Next, please. So to study this, we plot the variance with respect to the rest frame wavelength, and we use the data from the Zwicky transient facility, and also we are using the quasar sample for this study. So in this plot, we find an anti-correlation between the variance versus the rest frame wavelength. And to know more about this project, I would like to invite you to visit my poster. Thank you.
Many thanks. And our last poster presented by Omar Kurtante. Please go ahead.
I don't see Omar connected, so he might have had some issues. So I think we can move on to the next, to the discussion.
Oh, okay, no problem. So, well, many thanks for such interesting posters. And, well, I encourage the audience to have a look at these posters in Slack and leave your questions and comment there. And so, as Roberto said, we can move on the last discussion session. I think that we have around half an hour to discuss. Well, there were many interesting talks and exciting results, so there are many interesting things to discuss. I posted, I don't know if you saw in Slack, I posted some general topics to start with the debate, but please feel free to propose other ones during the discussion. Also, I encourage the audience to ask questions to the panelists. We have a great talk today, and the panelists are all experts in the theory of quasars and galaxies. So take advantage of this. What I wanted to do is to share my screen to show the slides with the questions that I prepare, and they are also in Slack, but I would like to share the screen in case someone is not connected to Slack. So let me see if I can share my screen. Can you see my slide?
Yes.
Yes. This question are also in Slack, but just in case I prepare these slides. As you see, the first topic that I would like to discuss is about the main questions that simulations and models need to tackle more urgently. Considering the accelerating progress in the observational studies of quasar and different redshift and the advent of new observational facilities, I think that it is very important to develop models that can explain those observed properties and can make predictions that could guide the future observations. So I would like to ask, which are the main questions that require to be tackled more urgently with the theoretical models in order to contribute to current and future observational studies. I prepare some ideas, as you see. For example, during the conference, we have mentioned that some of the most challenging problems are related to environment of quasar as a function of mass and redshift, but very especially at high redshift. Another important issue mentioned during this conference concerns the role of AGN, for example, quenching, as we saw in our last talk, on the determination of the properties of host galaxies and their neighbors at different redshift. And we also discuss about if AGNs contribute to quenching or in other cases can enhance the stellar formation of galaxies. Well, another important topic discussed today and in some talks in previous day is the formation channels of first quasars. Determining which are these channels could be a key question, and is one of the greatest theoretical challenges, in my opinion. So, in particular, the detection of supermassive black holes at very early times imply a very rapid growth that models should be able to explain. And well, perhaps another interesting question, in my opinion, is the role of AGNs on the reionization of the universe. So I would like to know if the panelists have any comment about this point, or would like to raise another topic related to this, or if the audience have questions to the panelists regarding these points.
I see Joanna has her hand up.
Yep.
I have some problem to see the participants who raise their hands. I would like if the assistants can help me, because I don't know why, but it's difficult for me to see the participant who raised the hand.
So if I may say on a galaxy quenching oriented perspective, I think one of the biggest questions we want to answer theoretically right now, and we should focus on, is reconciling or connecting the two scales at which AGN operate, because we do have GRMHD simulations with successful jet launching, so we know, if you will, the micro scale physics of how AGN operate. However, we do not yet have a good consistent connection between these GRMHD simulations and, say, cosmological zoom-ins. So I think from a quenching perspective and understanding the true interaction between gas in galaxies, AGN, and potential star formation processes, I think bridging this gap in large scale and small scale understanding is the most pressing matter, theoretically.
Yes, I also think the same. And also link simulation at very high redshift with those focus on the lower redshift universe. Any other comment?
Yeah, so I think a key question is, how do we do this, right? How do we go from the small scales to the larger scales, right? Even in simulation, it's very hard. I think there have been some progress where you have your large scale simulation and you're getting a higher resolution in the centers of galaxies, for example, but still, I don't think it would be enough to solve what you're talking about, right? So it is hard.
Thank you very much. Another question, or comments. The audience can also take the opportunity to ask questions to the panelists.
I'll just go ahead and jump in the meantime and say I agree with what Melanie said. And I also wanted to add a point about one of the bullets on your slide, I think one of the challenges that we should be focusing on is not just the formation of the first quasars, but this question that was brought up several times about what does the rest of the AGN population look like? What does the rest of the black hole population look like? You know, because clearly we're only seeing the bright tail at redshift 6 and beyond. So I don't have any great ideas about exactly how to go about that, except just to keep working on these models and try to build better models of black hole growth and formation.
Thank you very much. Any other interesting topic to tackle with simulation in the next years that you consider that it is important to mention now? Or if the observers have any topic that would like that simulation address or try to address with from the theory. No. Well, so then we can move to the second topic. As I said, all these topics are in Slack, but I can share the screen for those who are not connected to Slack. So, well, I don't know. Can you see my screen?
Yes, we do.
Yes. Well, so the second topic is about how to improve simulations. So in order to successfully achieve the goals mentioned in the first topic, I would like to ask if you think that current simulations and models are enough, or should we improve them? And in the later case, how can we do it? Which are the next steps? For example, during the conference, some people mentioned that we should run simulation in larger volumes. Also, perhaps in some cases, it would be important to increase the resolution. In particular, which is the best balance we can reach in next year between resolution and volume, because if we increase both, the computational cost will be higher. So what is the most important? I think, for example, to increase the volume, but perhaps it does for some purposes increase also the resolution, and which is the priority, resolution or volume. And perhaps improvement of the subgrid models for AGNs, feedback, for example, especially also the subgrid model that are related to black hole growth. Also, I think that it could be relevant, the revision of black hole seeding prescription. I don't know, for example, how much freedom do we have in selecting quasar environment and populate them with black hole seeds, which is something that people asked in previous days, and which galaxy properties should be important to determine the black hole seeding, for example, halo mass, gas metallicity, gas mass. Another important thing that I think it should be relevant is to revise the way we calibrate model parameters. Perhaps it would be worth include more constraints given by observation at high redshifts. And I don't know, for example, if it is okay to use a similar model to use for local galaxies which are calibrated at against local properties. Well, these are the question that I have in mind, but please feel free to mention another thing that you consider that that is important to improving models. So please, I don't know the opinion of the panelists about these issues. anyone has any opinion, any comment about what is the, for example, what is the most important thing to solve from the, or improve from the theory?
I think the dynamics of the black holes. If I would have to pick something, I think it's key that now we're trying to, and we have seen this today, right? That we're trying to connect really the dynamics of the black holes following a galaxy merger, and I think that would be key for LISA, but also for understanding of when is the agent activity actually showing up during the merger and things like that. So I think for the subgrids modeling, I think this is key. Yeah.
Okay. And for example, for the modeling of for subgrid modeling, which is the most perhaps important things? For example, if we want to improve the black hole seeding prescription, what will be the way that we can accomplish this? Because now I realize that there are many approaches for black hole seeding, and I don't know which will be the next steps.
Sorry, Maria Emilia, we have two hands raised, one by Madeline Marshall and
Thank
by
you.
Akran Bomink.
Shall I go first? Is that okay?
Please.
Yeah, I just, in terms of the question about which is most important, I think obviously better resolution would be awesome. Better volume would be awesome. But at what point are either of those things really important if we're missing really important physics? So for example, in Melanie's talk earlier, she compared all of those really state-of-the-art simulations, and they all showed very different things for what the black hole stellar mass relation would look like at high redshift. And so is there really a benefit of pushing these other very important but difficult problems if we're still very unsure about, like, each of those simulations is so different? So which one and what is the best one to actually push forward in this way? So I think the key, at the moment, in terms of what's missing, it is understanding which of those subgrid physics, what's missing, what's the best model that actually reproduces the observations, and then perhaps going and having the same issue, I guess, over and over again as you push to higher resolution as well. But yeah, that's what I think.
Thank you. There is another hand which raised, or?
Yes, I was just going to agree on the points raised by Madeline. I think we need a combination of both high resolution simulations and larger volume simulations to be able to solve these problems. And I think in terms of development of subgrid models, we already have an extensive amount of simulations where the approach has been to calibrate against established observations, particularly at low redshifts. I think a very useful and independent approach, alternative approach, would be to use not completely do away with calibration against observations, and instead construct a nested set of simulations at different resolutions, where the higher information from higher resolution simulations can be used to inform subgrid models at lower resolutions. And we can create basically like a ladder of simulations at these different resolutions. And I think a lot of groups have already pursuing this approach. For example, the small collaboration. I think that would be a very useful approach, which can kind of at least partly deal with some of the uncertainties and different results that we are getting from different simulations. So.
Yeah, regarding the volume, for example, I understand that many people mentioned that the volume should be around 1 gigaparsec, the simulated box. But and the resolution, according to what I understand from previous talk, is that the resolution could be the same as, for example, the resolution in Eagle or TNG at the moment, but increasing the volume but preserving the resolution. I think that this is the current approach. And if you want to increase more the resolution, then you don't. Then you have to use the zooming technique. I don't know if someone can comment on this.
Yeah, I can say a few words. I think what everyone has sort of said or hinted at is, there's no one best way forward. It's not like we should, all drop everything we're doing and run one kind of simulation, right? This is just because it's such a huge dynamic range that we're trying to simulate, and a huge range of questions we're trying to answer. Like it's always going to be an iterative approach, of pushing the resolution and then building better physics that you're now resolving explicitly that you weren't before, but better physics prescriptions, and balancing between getting the cosmic variance pinned down and getting good statistics from large volume simulations versus being able to actually resolve things explicitly. And so I think we absolutely need both of those, and need groups working on both of those. I'll also say, I think Melanie's right that black hole dynamics is a really important part of this that I think has been left behind, I think, in a lot of development of in terms of development of new models, because it is a really difficult problem, right? I mean, repositioning is stuck around this long for a reason, well, several reasons, I suppose, but one of them is that it's a really hard problem to do directly, and so we've seen has been a lot of great progress on that in recent years. But I think it's, there's no one thing you can tease out, right? Like if you want to model black hole dynamics, then you also need to be modeling, formation and feedback and accretion well, because they're all going to be interconnected, especially as you go to smaller and smaller scales.
Okay, yes, thank you very much. And well, another of my concerns is regarding the calibration of model parameters. Because many simulations constrains the subgrid model parameters using observation at a low redshift because they are the ones that are more known from the observational point of view. But if we want to analyze a high redshift with those simulations, perhaps this can be problematic. So I was thinking if it would be possible to start constraining the model parameters by using observation at higher redshift. What do you think?
Can I jump in on this? So in general, I think, like in terms of calibration, it should be done against observational measurements which have the least amount of uncertainties. And currently at high redshifts, we have significant amount of uncertainties in terms of our observational measurements. So I would not personally be too favored towards recalibrating everything towards high redshifts. And at the same time, in terms of current calibrations which are done at low redshifts, I think it's an extremely good test for our simulations which are calibrated at low redshifts to be able to try to reproduce observations at high redshifts, because if they're successful at that, then it's a very, very strong test, in my opinion, that the simulations would pass if they are able to successfully do it. So I think maintaining that calibration could provide very strong constraints when you compare the same simulations at higher redshifts. So in my personal opinion, I think if we are calibrating against observations, then we should continue to do that at lower redshifts.
Perfect. Yes. So we are not ready to start using high redshift observations to constrain simulations. Yes. I think that yes, this is a good point. Yes, perhaps we have to wait that we have more less uncertainties at higher redshift in order to start to do to use this kind of approach. And well, is there any other point that you consider that it is important to mention, to take into account to improve theoretical models in the next year? No? So, well, we can move to the last topic that I propose. I would like to share my screen. This topic was also uploaded to Slack. So, well, I would like to ask what difficulties can we find when comparing simulation models and observation at different redshifts, and can we address them? For example, possible difficulties are selection effects in observation that should also be taken into account to select a simulated sample in order that the comparison is fair. Also, another thing is mainly at a lower redshift, the aperture effects associated with different instruments. Also, the spectral energy distribution modeling, and in the case of high redshift galaxies, perhaps it could be very important to know how to model dust, because there are many uncertainties regarding the nature and distribution of dust at high redshift. So what do you think about this point, how we can address them, and or if you have any other one that you want to mention, please feel free to do it. I found that, for example, in my research, these are the more important points at the time of comparing simulation with observation, but I don't know for other kind of studies if there are other things to take into account.
Well, I'll go ahead and add radiative efficiencies of accreting black holes to the mix. I think that's a big one for these high redshift black holes, where we don't know if they're, accreting at super Eddington rates and have lower radiative efficiencies because of that, or some other accretion mechanism that's different than what we envision for black holes at lower redshift. And so that makes a huge difference into our understanding of how black holes form and grow at early times. And I think, Lisa will help put some constraints on the black hole mass distribution at the highest redshifts, but I think also just the more we can constrain as I said, the faint end of the AGN luminosity function at higher redshift, that'll allow us to constrain, the growth history of the black hole population more generally.
Okay, and thank you. Any other comment?
There's a raised hand by Chris Richardson.
Thank you. Yes, I would need help to see the raised hand, because I have some problems. When I share my screen, the participant list disappears, so I am not, I don't see the hands. Well, please go ahead. I don't know who raised the hand.
Yeah, so I'll just, echo what Laura was saying there, that knowing these accretion rates for black holes really helps in terms of the photoionization modeling as well, because when you're predicting the ionizing spectrum from the black holes, largely a lot of the parameters are degenerate. The black hole spin, the accretion rate, the black hole mass, they all affect the SED in similar ways. And so these next generation X-ray observatories will help provide important constraints on that. And I think also from a modeling and observational perspective, we need to be careful about X-ray binaries, because X-ray binaries can mimic the activity of low mass black holes. And so disentangling that emission can be a difficult task. And so some of that comes down to looking at low metallicity dwarfs and constraining like the X-ray luminosity metallicity relationships, and then incorporating those into models as well.
Thank you. Any other comments, questions?
I think I'd like to add how important it is for theorists to place things in the observational space in order for us to have legitimate comparisons between what we see with the observations and how that actually relates to the physics. So for example, if we're trying to measure the black hole stellar mass ratio in the early universe, the overall black hole population has some relation, but you're only going to be observing the brightest quasars. And so how does that actually, how would we observe the things that we theoretically predict? And so selection effects are a huge issue when it comes to AGN. We're not detecting faint ones. It's all of the very, very bright stuff. And then when we detect the bright stuff, we can't detect the hosts. So it's there's this selection effects are really important, but then also putting it on in terms of like mock images and things. So the properties that we measure from the simulations are obviously very different to properties that observers measure. So we would talk about stellar masses and bolometric luminosities and things, but when you're actually going out with your telescope, you're observing in some band. There are lots of uncertainties and lots of noise and PSF effects and resolution effects. So we've been looking recently at galaxy sizes and how just different instruments would give you a completely different galaxy size because of the instrument effects. And so trying to actually push our simulations into the observer space so that we can actually do those comparisons is really important. Obviously, we can come from the other side and try and push our observations into the theoretical space. So, deriving stellar and black hole masses from your observations, but, we can go both ways.
Yes, observers try to obtain, for example, stellar masses or output of simulations, and yes, also people who work with simulation try to predict the observables. Yes, and we have to find a balance between perhaps we can find each other in the middle. Yes, I think that it's a challenge from both point of view, and yes, it is worth that observers try to predict quantities obtained in the simulation, like for example stellar mass, metallicities, but it is also important that theorists try to generate the spectral energy distribution and images, synthetic image of simulated galaxies in order to perform a more straightforward comparison with observational works. Well, any other comment about this?
I think we should. Oh, sorry. I was just going to say that I fully agree with this, and I think we should do this before running any more simulations, because we already have this diversity of modeling of simulations, and we should fully exploit them before actually doing, next generation simulations, by doing all those, mock observations, and before even putting more physics. We should do, more, apple to apple, comparisons with observation first. This would probably, makes more sense.
Yeah, sure. Well, I think that at least we cover the 3 topics that I upload in Slack, and we are almost on time. But if you have any other quick topic to end this session, please let me know, or the audience, if any participant want to ask, take the opportunity to ask any question to the speaker that they couldn't do before. Please, I think that we have some minutes. So, well, I think that we can conclude the session today. The three topics that I propose are related to enhance the collaboration between the people who work on theory and observation. I think that we should first decide which are the main topics that observers consider important for the next year to be tackled with simulations. Then we should see if our current models are enough, or we need to improve them in order to tackle such issues. And finally, once the models are ready, then we should decide how to compare the simulation with observations in order that the comparison is consistent. So I hope that the interaction of people working in simulations, models, and observers improves in the next year, and we obtain a very exciting result for discussing in future meetings. Well, so finally, I would like to congratulate the organizing committee for such an exciting meeting. Also, the speaker, the talks, all the talks were very, very interesting, and I am very happy about this. And I am also consider the Congress was very fruitful with many participants, and well, I think that it was a great success. So congratulations to organizer, participant, speaker. Well, thank you very much.
Thank you very much, Maria Emilia. Yes, so I think this is the final session then of this conference. And just wanted to, before we finish, just wanted to thank everybody. So particularly I want to thank the SOC and the LOC for all the work in getting this meeting together. Thank particularly Ana, Liang, Sofia, and Manuel for helping backstage with all of the talks throughout all of the sessions. Want to thank all the 8 invited speakers, the 40 contributed speakers, and also the 40 poster presenters for great contributions. I think you really made the conference great. It was, I think it was also, I also think, just like Maria Emilia, was really a success. And particularly I want to thank all the attendees. So thank you very much. It was really encouraging that despite the fact that there's so much dispersion in the time zones, there were about over 100 people connected at all times for most of the sessions. Thank you. Want to thank, of course, sorry, I should have mentioned all the moderators of all the sessions, and in particularly for those that led the discussion sessions that were fantastic as well. So there's been a lot of discussion, lots of really interesting questions, and we can keep discussing in the Slack. So if you have anything else you'd like to add, it's been already very lively, and I'm sure it will continue being so. So again, just thank you very much. Thank you to everybody, and well, have a good rest of the week.